In this video, we'll talk about a proof by contrapositive, also known as an indirect proof. So when we talk about proofs, there's indirect proofs and direct proofs. They're actually very, very similar, even though they sound like they should be opposites. An indirect proof is a direct proof of the contrapositive. So by doing an indirect proof, we also cover direct proofs. So let's jump right in. So what we have here is we have an example. We're trying to prove if x times y is irrational, then x is irrational or y is irrational. So this one is a little difficult to work with because basically irrational, our best definition for it is it's not rational. That's really the best way we have to describe it, which makes it really difficult to work with. However, if we write the contrapositive, which remember, contrapositive is not C implies not H. So I'm looking at my old statement. X is irrational or Y is irrational. Remember, if we negate an or, it becomes an and. So this we could say is X is rational and Y is rational. That would be our not C from our original statement. Now we're going to look at our original hypothesis. So if x times y is irrational, if I want to negate that, it would be x times y is rational. Now I'm looking at this contrapositive and I'm already thinking to myself, this is much easier to work with. I can work with a rational number because I can set it equal to something as opposed to an irrational number where it's not equal to something. So if I prove the contrapositive, I have then proven my original statement because they are both logically equivalent. Now let's take a look and see how we could prove this. So if we are looking at a proof, so this is your more stereotypical proof, you start and you just start listing off your hypothesis. You kind of let all that happen. That much is still very similar to proof by contradiction. So we're going to let x and y be rational. That's my hypothesis. That's what I get to start with. I'm just saying, okay, let's talk about two rational numbers, and then we go right into what that means. So this means that then x is equal to some a over b, and y is equal to some c over d. And we can say this because this is the definition of a rational number. Oh, and I forgot to include in this here, a, b, c, and d are all members of the integers. Now I have to sit here and I have to think about what I need to show, which is this. I have to take x times y and I have to show that beyond all doubt it is rational. So I have to use this definition right here for x times y. If I can prove that it's an integer divided by an integer, then I have proven that it's rational. So we're going to go ahead and we're going to say, okay, if we have x and y already set up, then x times y is equal to a over b times c over d. Just substituting in those values. So if we were to give a reason for that, it would be substitution. Which then means we can say x times y is equal to ac over b times d. And now we can look at these individually and we can say, since a times c is an integer, and b times d is an integer, basically I'm using the definition. Remember, it's a biconditional statement. A number is rational if and only if it can be written as an integer or as a fraction involving only two integers. Since I have an integer divided by an integer, we can then say this implies x times y is a member of the rational numbers. And at this point, I have shown what I want to show, and I can end my proof either using a box or the letters Q, E, D. Either way is fine. Now you might be thinking, okay, this is a shorter proof than our contradiction proof, and it is. Direct proofs usually are shorter. However, sometimes it can be a little difficult figuring out, what do I do after this? Where do I go after letting my hypothesis happen and maybe talking about some definitions? It can be a little difficult to discern that sometimes. So sometimes a contradiction proof might be longer, but you do have a roadmap to kind of help you, to help guide your thinking, and then maybe it'll even spark a way you could do a direct proof, or an indirect proof as the case may be. Now, indirect proofs, direct proofs, like I said in the beginning, are very similar. So this, what we've done right now, this is a direct proof of the contrapositive. And since we've proven the contrapositive, that proves the original statement true. That's what it means to be an indirect proof. I'm not proving the statement itself, I'm proving the contrapositive. And if I had the original statement being what our contrapositive was, I could still apply all of these thoughts, and I could make all of this still possible. This would be a direct proof in that case.